Okay, here we are. So Juan Tomás Vázquez is a graduate in geology science at the University Complutense of Madrid, and he received his doctorate for the same university in 2001. But in 1986, he joined the Marine Geology Service of the Geological and Mining Institute, IPNA. Between 19 and 2007, he was the professor at the University of Cadiz, where he taught marine geological and tectonic. Since October 2007, he's a senior scientist at the Spanish Institute of Oceanography at the center of Málaga, forming part of the Marine Geoscience Group, GEMAR. His line of research focused on the study of the active geological processes in continental margin and ocean basin, active geomorphology and tectonic fluid emission for the subsoil, mud flow processes, and tsunami generating mechanisms. Since 1986, he has participated in more than 50 national and international scientific campaigns. He has authored numerous scientific papers, publishing the book and journals, etc., more than 33, and with more than 250 contributions in the national and international conference. So, Juan Tomás, I'm going to pass you the ball, and you can share your screen with us.
I'm going to talk about the work that the Spanish Institute of Oceanography did during the volcanic eruption of La Palma to control the changes in the seabed generated during La Palma 2021 eruption, mainly related to the advance of lava flows to the coast and submarine domain to form lava deltas. This is the index that I will use in this presentation. First, a short introduction, objectives, methodology, and finally the main part, the monitoring seafloor changes and main results. Firstly, some remarks about the geology of the island. La Palma is made of two main volcanic edifices. The northern one is an older sea volcano, and the southern one is a big volcano that corresponds to the active zone of the island known as the Cumbre Vieja Ridge. On the left side, we have a large map of the Cumbre Vieja Ridge, and you can see how the date of the rocks are younger than 200,000 years. And in this second map, the historical eruptions have been represented in orange with the last one in red. You can see a similar pattern with the mission center close to the axis of the bit, and the formation of lava flows preferentially to the west, with the formation of lava deltas when these lava flows arrive to the sea. Another interesting aspect to take account in the morphology of the island is the development of large landslides. When a volcanic edifice grows vertically very quickly, the stability of its flanks also increases, and large landslides can be developed. On the island of La Palma, the large landslide of the western flank stand out and control the morphology of the flanks that are very sloped. Well, on September 19 of 2021, a volcanic eruption began on the island of La Palma. To control the changes caused on the seabed and the water column during the eruption, two main oceanographic cruises were carried out on board the research vessels Ramón Margalef between 24 September and 3 of October, and the Ángeles Alvarinho between 17 and 30 of October. Both vessels from the Spanish Institute of Oceanography, to carry out a multidisciplinary oceanographic study of the southwest area of the La Palma Island, with special attention to the analysis of the morphological changes in the seabed and coastline, as well as to the possible emission of gas of volcanic hydrothermal origin, in addition to studying the effects of the lava flows on the morphology of the seabed. Finally, a fourth control cruise was carried out in February 2022, which was the importance of monitoring the growth of lava deltas and the progress of the seabed from the point of view of volcanic emergency management. Well, when hot lava enters the water, it bursts into pieces, building a new land on the ocean edge from the fragment material, forming the so-called lava deltas. These bodies are normally built by a pile of gravel that are formed by hyoclastic breccias alternating with lava flows, deposited parallel to the slope of persisting topography, forming a foreset. And then is covered by a topset of lava flows, aerial lava flows, forming a bench that gives a false impression of solid ground. This configuration makes these bodies sound unstable. Planes of weakness could be generated and instabilities from this internal anisotropy of the foreset, and could induce the collapse and slippage of sector of these deltas. During these events, the hotter interior delta comes into contact with seawater, generating hydromagmatic explosions with the expulsion of lava splatter and large rocks. Also, emission of high temperature gas and large waves of the scalding water on shore could be generated. These are examples of lava delta collapses in relation to the Kilauea lava flows. They are cartography the previous lava delta and the collapse that suffered this delta in the Hawaii island. In the lava delta La Palma, this process had not occurred on a large scale, but some hydromagmatic explosions can be observed, such as the one seen in this video recorded by the Professor Ramón Casillas. We have mainly used two techniques in this study: the acquisition of high-resolution multi-beam bathymetry data with a MB710 echo sounder, and the observation and direct sampling of the seabed along transit carried out with the ROV Leuropus 2000. That allow us to identify and characterize structures associated with active processes, analyze the morphology changes and the evolution and submarine advance of the lava flows. This echo sounder, this multi-beam echo sounder, makes possible to obtain a bathymetric corridor of 400 beams with a width of approximately 2.5 times the depth. It allows obtaining bathymetric mosaics, making 3D models, and applying these GIS tools at slope, orientation, roughness, that improves knowledge of the morphology and the changes of that morphology may have through the erosion. The ROV allows us the visual recognition with high resolution cameras and the sampling of both rocks and loose particles with articulated mechanical arms to characterize the type of materials that are being deposited in the underwater environment. This is an example where you can see a maneuver where the ROV is taking a sample, and then Eugenio studied the sample on board. We follow a double strategy during these oceanographic cruises. In first place, the area between Tazacorte Harbor and La Bombilla, in the left part, was chosen as the most probable area of arrival of lava flows into the sea using the numerical model of lava flows from the National Geographic Institute that established how the lava flow could be on the surface of the island. In front of this area, we carried out a bathymetric survey at a 1 meter resolution from 15 to 500 meters depth. In addition, the deformation model obtained from satellite by also IGN allow us to observe an important deformation on the southwestern flank of the island. In this area, we carry out a bathymetric survey in front of the island to locate possible volcanic or hydrothermal emissions with a resolution of 5 meters up to 1,500 meters depth. A complete mapping and characterization of the seabed in the western part of the island of La Palma before and after the arrival of the lava flows to the sea was carried out. This is the bathymetric map that we made on the western flank of the island up to 1,500 meters depth, characterized by its steep slopes and as a singular point, a singular feature. This is a volcanic cone located to the southwest of La Bombilla that is an evidence of an ancient submarine erosion on this island. The lava flows reached the western shore of the island on September 28th, and later, this is the first area where the lava flows arrived. Finally, they form a southern lava delta attached to the northern of the lava delta or generated during the 1949 erosion, and a second delta located to the south of Tazacorte Harbor. First, we did a bathymetric survey in the probable arrival zone of the lava flows to establish the pre-erosion characteristics of the seafloor that has served also as the basis for determining the changes caused by the arrival of lava flows on the seabed. In this morphological map, interpreted from this initial bathymetry made by Alex Brenes for his master thesis, it can be seen how the submarine relief was characterized by a very narrow insular platform, insular shelf, in the area where the lava flows were going to reach the sea. The rest of the slope is characterized by erosive features. In the area where the first arrive of lava flows, it's characterized by a series of submarine gullies whose headwaters intersected the shelf, also very shallow. The shelf border in this area is around 40 or 60 meters. In the right hand, you can see 3 bathymetric profiles of the area where the lava arrives for the first moment to the sea. This is the final bathymetry map obtained during the first cruise on October 3rd, after the formation of the southern, the first event of the southern lava delta. On the right, we had, on the right, we had the bathymetric map at the end of the first cruise, compared to the initial bathymetry on the left. We can see how the seabed near the lava deltas was modified. After practically occupying the insular shelf in this sector, the lava flows were preferably channeled through the submarine gullies. These are the maps of bathymetric difference that we made taking as reference the initial bathymetry. On September 30, we saw how the material from the erosion are in the submarine gullies reaching 120 meters depth. On October 1, the arrival is already widespread, reaching a depth of 250 meters, and in October 3rd, the submarine front on the delta has been consolidated and the new materials reach a depth of 300 meters. This is the final bathymetry map obtained during the second cruise in October 29. In this case, On the right, we know how the bathymetry made at the end of this second cruise, and we can see how the relief associated to the submarine gullies in the upper segment of the slope is very smooth. In the data acquired in the cruise, we observed that the lava flows follow a similar pattern. Gullies are filed and appears new inputs. The new materials reach in this moment a depth of 360 meters. Always taking the bathymetry carried out on September as reference, these are the mass of bathymetric difference that we made in the second cruise. In the 19th of October, the situation was similar, but the accumulation thick was increased. On October 24, we appreciate that a new lava flow set seemed to be arriving from the north in this area. And on October 29, we were able to map this new lava flow as well as flows to the west and to the southwest that overflows the gullies when these gullies are filled. This is an interpret flow pattern through the October 29 bathymetry. Lava flows follow submarine gullies. In the first moment, this is the initial bathymetry. This is the new bathymetry. Lava flows fill the gullies and then overflow and flow down a slope, looking the best way to flow. Also, these are a comparative of 3D bathymetry models of the initial survey and the bathymetry obtained in October 29, observing how the submarine gullies in this area were filled, and even the generation of the relief over these gullies. That also can see in bathymetric profiles realized before and after the lava flows in this area. Finally, this is the bathymetry carried out once the erosion finishes February 2022. And in the right part is the map of difference of in the southern lava delta sector regarding to the initial bathymetry. We can observe the last phase in this area of growth of the southern delta to the south of the first arrival, following a previous depression. You can see here is the depression in the self. As a summary, it can be seen the insular shelf will be occupied by the lava delta, except in the southern area where lava flow has been channeled into a previous depression on the outer shelf, while on the upper slope, lava flows taking advantage of the presence of submarine gullies to drive the flow.
2 minutes.
This is the main flow, secondary flow in the north of the southern delta, and this is the final lava flow input. Now let's see what the seabed occupied by lava material looks like in the video recorded by the ROV. This material advances along the seabed, both as blocks, flows, and as megapyrolavas flows. This is a summary of the transect made from deep to shallow waters. First at 291 meters, we observe as and possibly hyaloclastic deposits. And when we ascend the blocks, flow appears. This is the ROV maneuver taking the particles, the minor particles, and now, yes, you can see the blocks flow that appear around 277 meters. Also, with appears pyrolavas. And in more generalized, in a way more frequent, the development of mega pyrolavas at 120 meters. Well, this is the maneuver of taking samples. It should be noted that the video is in color, but other rocks are blacks, as we see before. In the video image, we see different shades of gray depending on the different brightness of the material. This is a main mega pyrolava. And finally, near the deltaic front is the next sequence.
Juan, you only have 1 minute.
Bueno. Si pudiera avanzar el vídeo, iríamos mejor. And finally, we can see the rocks of in the front, in the deltaic front, that predominates hydroclastite breccias around 45 meters. This is diagrams prepared by José Antonio Lozano, where the two main types of lava facies that have been recognized are described, the flows and the horopyro lava phases. This, I would also like to point out the effect of the fall hydroclastite and ash deposit in the submarine front of the delta, but also in adjacent areas of the island that produce an important tapestry on the seabed. As final ideas, these are the two dominant types of lava deltas. The upper one is generated from the predominance of aerial lava that generates alternating hydroclastic and pyrolava forest sets in the delta front, while in the lower case, subaerial types lava predominates that generates underwater stacks or laminar lava flows. In La Palma case, we have a mixed type with a predominance of aerial AA lavas, also the presence of lava tubes, also the formation of pyrolavas, allow the formation of pyrolavas into the piles of hydroclastic breccias in the submarine domain. In addition, the presence of a 100-meter cliff on the coast was determining in the first moment. It caused the lava flow to break in the higher part of the cliff, and the lava will descend toward the sea in the form of blocks. Although they evolve into channeled flows later. This video is longer, but only we can see the first part. I just want you to see the subaerial morphology of the lava delta, and that the lava flows from the cliff was not always continuous to the sea. In this area, you can see how fell in large blocks or drops of viscous lava from the top of the cliff. And this is all. Many thanks.
Thank you so much, Juan Tomás Vázquez from IEO in Malaga. Any question? Yeah.
Thank you for your presentation. I have a question about lava doses and how they can collapse. I was wondering if you know if they are being monitored to try to predict a collapse, if so, how?
Do you understand the question?
I don't hear.
Si has visto
Sorry.
algún tipo de colapso en el lado delta.
In this, in our lava deltas, I can locate some collapses in the submarine front, not not in the upper part are no well stabilized, but in the submarine front we are find several minor landslides affected the lava front, but no calculate the volume.
Okay, thank you so much. I think we have to pass to another speaker. Thank you, Juan Tomás, again
For your talk.